So this is, I guess, a centennial tutorial talk about magnetic microscopy. So I'm going to just try to give a general overview of kind of different instruments and different processing protocols that we have for magnetic microscopy, give a couple examples, and try to tell you a little bit about how you can maybe use it in your own research. So hopefully this can give us all, give you some ideas. Okay, so just like a very general introduction, why do we want to do magnetic microscopy? Why do we want to image magnetic fields at sub-millimeters kind of scales? The general reason is that a lot of different rocks have very complex multi-generational magnetizations. All right, since there are so few people here, why don't you just interrupt with any questions? We're gonna have like a discussion section. All right, so anyway, so so one example here are these chondrites. So these are basically like space sedimentary rocks. They have these kind of millimeter scale clasts called chondrules, and other types of clasts as well. So some of them contain these like primordial iron grains, which are formed during chondrule formation. So before the accretion of this asteroid body. But this stuff is surrounded by this black stuff, for example, this fine-grained matrix, which is also very magnetic. And that stuff is from a different place in the solar nebula, and it also could undergo aqueous alteration on the parent body, for example. So we have different generations and formation origins of magnetic material here versus here, and they're only separated by kind of 100 micron distances. So if we just measure the bulk material here, you're kind of mixing these very different signals and generations of magnetization. Another example here, which I talked a little bit about yesterday, some of you guys might have seen this, Speleothem. So these are cave deposits. Usually we try to measure stalagmites. So they've been prized by the kind of paleoclimate proxy community because they can potentially record environmental changes through time. But that, of course, also means that these changes occur at a fairly small length scale. So in this case, you kind of have millimeter or sub-millimeter size annual banding. So you really need to resolve things at a sub-millimeter scale to really understand the time series of what's recorded here. So I'll talk about a couple different technologies. Probably the two most mature, at least for geoscience applications, are the SQUID microscope and quantum diamond microscope. So here's just the images of two examples of these. On the left, that's the unit at MIT, the SQUID microscope. On the right, that's the Harvard quantum diamond microscope, QDM. So I'll just take a few slides to talk about what these instruments are, what they're capable of, and then kind of go back to the examples I started talking about earlier. Okay, so they work on very different principles. SQUID microscope uses a SQUID sensor, so it's cryogenic. It's mounted at the tip of this little rod, and it's put actually, when in operation, this is cooled down to 4 Kelvin, so it's under a insulating vacuum. And the sample, and it makes a point measurement. So the sample has to be moved, kind of rasterized below the sensor. And because the samples are room temperature, there needs to be some separation between them for the insulation. So you got 200 microns roughly between the sensor and the sample, and that kind of limits the resolution of the SQUID microscope to about 150 microns. So the QDM is a solid state sensor. It's room temperature. So you can put the sample, which is on this little disc here, all the way up to the diamond, which is the sensing element there. And you can get resolutions down to about a micron. So it's limited by optical diffraction limit. Okay, so the resolution is very different. And another property of the QDM that makes it very suitable for these high resolution imaging is that you can, because it's an optical detector, so you can actually image your sample optically and magnetically using the same camera. So you can register the correspondence between features and magnetic signals very precisely. On the other hand, the SQUID microscope is not an imaging sensor, so you can do things like put these little tags in. So these are literally pieces of printed ink that correspond to these dots. So by doing that, you know where your samples are. This helps a lot with registration between the sample image and the magnetic image, but you're looking at somewhat more uncertainty there, maybe tens of microns. So why do we still use a SQUID microscope? Of course, it's because the DC field sensitivity is orders of magnitude better than the QDM, so about 2 to 3 orders of magnitude. So these are just two maps of basically blanks. You can see the type of noise is also quite different, but the main point here is that the color scale here is a lot bigger for the, a lot smaller for the SQUID microscope. So it's got a lot less noise. Okay, so just to summarize that, the QDM has much better spatial resolution, better spatial registration with the sample. So it's very well suited for high resolution identification of where your sources are. The SQUID microscope has much better noise floor, and it's easier to make a bigger field of view on a SQUID microscope, although you can do it on the QDM as well. You just need to take more time. If you actually want to build your own unit, there's more. You probably should know that the SQUID microscope is much more work intensive than the QDM to maintain. It's cryogenic. It breaks often, less often than it used to, but the QDM is quite robust. But the good news is, if you don't want to build your own instrument, both of these instruments are actually available to some extent. There's a number of SQUID microscopes in the world that are running, and there's one in France that's kind of coming online soon. The QDM is a newer technology, so it hasn't really spread that many places. So there's a working unit at Harvard, but MIT, Minnesota, UC Berkeley, and Utrecht all are in the process of building. So hopefully in a year they should all be working. And then there's another one at the Hebrew University, although that one has somewhat different specifications. So if you are interested in using these instruments, you can talk to these different institutions. Uh-oh. Oh, there we go. Okay, so going back to which instruments should you actually use, if either or both. So this is kind of graphically summarizing what I presented a few slides ago. So the QDM right now has something like a few nanotesla DC field noise floor, 1 micron resolution. SQUID microscope is much more sensitive, less spatial resolution. So they kind of occupy different areas in this space here. So the resolution is pretty easy to understand. That's basically just how close your sources can be before you can tell them apart. The sensitivity is a little bit more nebulous, I think. Right? What does 5 nanotesla DC field sensitivity really mean in practice? Hello. So it's for people coming in later, so this is basically a discussion section, I guess. So my talk's not even going to run 30 minutes. So if anyone has questions about anything I'm presenting, just speak up. Yeah. Oh, that's the magnetic tunnel junction sensor. It's kind of like we tried to use that at MIT some years ago, and there's a couple more units in Brazil and Cambridge, I guess, that's been used for rock stuff. But at least as far as I know, the QDM is better in every way, at least at this point. Okay, so so DC field sensitivity. What does 5 nanotesla DC field sensitivity really mean in practice? Okay, so I'm not going to talk about the derivation of these curves. I can, I guess, kind of wavily explain it if someone would like me to. But basically, basically you can generate these curves using the parameters in the last slide, like the DC field sensitivity and the sample sensor distance. So the QDM kind of occupies this space here. So because you can get your little dipole, your single domain magnetite right onto the sensor, you can detect some crazy moments with it. But the SQUID microscope's is more able to detect very weak rocks, like some weaker sediments like carbonates, for example, because of the DC field sensitivity. So put this in perspective in terms of moment sensitivity. So this is the total moment of the sample. The 2G SRM, which is the kind of standard cryogenic magnetometer, has a noise floor, kind of optimistic noise floor around here. The standard normal bore size unit. And then both of these instruments can, in principle, map to better moment sensitivities. In terms of the QDM's limitations, the biggest limitation actually doesn't come from moment; it comes from the per unit volume magnetization. So if you want to image something on a QDM at high resolution, that's the number you should pay attention to. So just to put some context into this, so these over here are single, magnetic grains, right? So they're kind of single grains are in the saturated state. So even with goethite, which is a pretty weak magnetic mineral, both of these instruments can easily detect these grains. The QDM is, of course, going to do it at higher resolution. So if you're going to look for where your magnetic grains are, the QDM is a good instrument for that. Now, if you're going to measure NRMs, so natural remnant magnetization, i.e. you're going to do paleomagnetism instead of rock magnetism, then you're talking about much weaker moments, and also you're talking about weaker intensities and higher moments, right? Because once you get below some threshold, kind of around this range, the moment isn't really statistically robust enough to carry any information about ancient magnetic fields anymore. So you're really in this range. So these are NRMs of chondrite inclusions, which are generally pretty strong. Zircons over here. I'll talk about some other weak sedimentary rocks later. So in this case, you have to be kind of careful if you're going to try to use the QDM, because not every natural rock is in the sensitivity range. The SQUID microscope, however, is pretty good about all these lithologies. Okay, so to summarize that in terms of practical usage, so the SQUID microscope can identify ferromagnetic carriers at the 100 micron scale. But a QDM can do this at the grain scale, which can be very useful. And then the SQUID microscope can recover natural remnant magnetizations from pretty much any common lithology. Or so the QDM is limited to kind of relatively strong samples. So let me go back to the two examples I had mentioned earlier. So this is the chondrites. So these, spherical chondrules, they formed in the solar nebula. They have these magnetic minerals, these really nice iron grains. So we want to detect a signal from these guys without any contamination from the signal from outside of this grain. And this might tell us about something about the magnetic field during planet formation. Okay, so this is, I think, a cool early example. It's actually the first paper where I think both of these techniques were used together. So it shows a nice way of complementarity between these methods. So SQUID microscope has lower resolution, but it's able to detect the bulk magnetization of this chondrule very well. You can kind of see the outline of the chondrule. I'm sorry if that's not clearer. And then the QDM, on the other hand, because at high resolution, you can see where the magnetic fields are coming from. So it's much harder to for example, construct a net dipole moment out of this map. And also, this is an IRM in this case. Although the NRM would have been detectable as well, but this is an IRM. So it's telling you where the magnetic grains are. And it turns out they match pretty well with where the dusty olivines are from optical microscopy. So that's good. So that's one example. So the QDM, again, for stronger samples, you can actually recover NRMs. So this is another class of chondrites called the CR chondrites. This is a big metal-filled chondrule from it. We don't really want to sample these gigantic multi-domain iron grains. So what we focus on are these very small, kind of couple 100 micron size, it's kind of exolved regions with iron, nickel, and iron oxide. Or sorry, iron sulfides. That has much better magnetic recording characteristics. So in this case, we isolate this little sample. It's about 100 microns, maybe a little more. That's the QDM map of the NRM. We can do an upper continuation, which means basically it calculates the magnetic field map if you were to measure it at a higher altitude from the sample. And what that does is it basically filters out the high spatial frequency components and isolates the dipole moment, which we can fit here much like the SQUID microscope data. Okay, so I skipped over a lot of steps here, but basically we can get paleointensities from these. Well, we can generate Zeiderveld diagrams, find components, and then do ARM, remagnetization experiments, and then basically generate a paleointensity. So Semarkona is the first meteorite I showed. It is an ordinary chondrite, probably coming from closer in the solar system. CR chondrites are coming from farther out. And we have these lower intensities in the CR chondrules. That's, broadly speaking, consistent with models of how the magnetic field is expected to vary in a solar nebula, but keep in mind this is just a model and quite simplified. But to first order, it does seem that both the general intensities as well as the drop is at least consistent with the idea that magnetic effects was important in nebular accretion and dynamics. So this is the range of magnetic fields expected if magnetic fields were driving nebular accretion in this manner. Okay, so to the second example, Speleothems. So if I were to plot that on here, Speleothems are extremely weak. So in an NRM, even 10 to the minus 5, 6 kind of range. So even for a SQUID microscope, actually some samples are not really measurable. But for QDM, it's pretty much hopeless at this point, at least. So again, what we can do is use the SQUID microscope, take advantage of its sensitivity and map NRMs. So these are actually little chunks of Speleothem that were sampled at MIT. And that's the magnetic field map that corresponds to these 6 little islands. So the reason you cut these islands is to help the inversion. So you basically get rid of the surrounding stuff around this little piece of Speleothem, and that isolates the magnetic moment signal and allows you to quantify the total moment more easily. So I'm not an expert in this particular work, but the idea here is as with kind of bulk magnetometry measurements on Speleothems, the point here is to try to look at paleosecular variations and magnetic excursions through time. So here's a different Speleothem from Brazil this time, mapped by the SQUID microscope. So you can see, in this case, there's 300 years of deposition here, roughly. You're looking at resolution kind of on the decadal time scale here. However, if you want to construct a higher resolution paleoclimate record from here, you might be better off using the QDM. So the QDM, I showed some of this data yesterday, you might have seen it. So this is the little box that corresponds to this map. So you can see we're resolving down to an annual time scale, or at least couple year time scale. But the trade-off, of course, this is not natural remnants, this is IRM. So this is just a way to figure out where the magnetic minerals are and try to use that as an environmental proxy instead of trying to understand their natural magnetizations. Yeah, that's right. Sorry. Yeah, so these two blue stripes are kind of those two. Yeah. Okay, so same map here. And this is the optical map. And again, you can do a very precise overlay here. And then we can integrate the magnetic signal across these bands to come up with the time series of the magnetic field intensity. And we can use that as a proxy for the magnetization in those bands. So this particular rock, again, is about 200 or 300 years. Well, it's 300 years total interval, but we're mapping really across a subset of it. So you can see how the magnetic field changes, or this is the IRM magnetic field changes through time. You can compare that to the 018 record. In the tropics, 018 is probably controlled by the amount effect, i.e. more negative means more precipitation. So you can see there's a nice negative correlation that seems to be consistent with the idea that stronger magnetization is deposited on these speleothems in times of higher humidity, higher rainfall. So most likely that's from just more soil saturation gives you more oxidation reactions with the bedrock that creates soft magnetite. Okay, so I'll just conclude there. But the point here is that the SQUID microscope and QDM allow imaging analysis of magnetic samples that are too weak or maybe too complex for traditional bulk techniques. I guess another little point I'd like them to stay on this slide. A little point to emphasize is also it's kind of a good byproduct, useful byproduct of the imaging, that you can look for the spatial distribution of your useful signals, but you can also look for the spatial distribution of contamination. So let's say you prep a sample, and there's maybe some sort of glass mount that you're putting it on. If there is any sort of contaminating airborne dust or whatever on that mount, the imaging actually can kind of resolve the signal you want and signal you don't want. So for many reasons, I think for very weak and very complex samples, these are good techniques. And yeah, they can be used for your own research if you are interested. All right, so should we have a discussion?
How do you keep the QDM in a field-free space?
Well, it's in a shield, like a shielded room.
Okay.
And it's got these Helmholtz coils.
Okay.
Yeah, so there's three sets of them. The other one does not. The other one is just massively shielded passively. It's got like, well, it's in a double layer shielded room, and it's got 3 more layers of shielding. Yeah, so, yeah, there we go. So it's in a giant can that's got a lot of layers on it. Yeah.
So what's the maximum fluidity for QDM?
Depends on how big the diamond is. So something like 3 millimeters. Yeah, so to get bigger than that, you had to do some tiling. You know, you take an image here and another one here, so on and so forth.
How do you set up AF for say your ARM experiments for feeling intensity? I mean, is it in line with the probe?
No, it's not. You had to take it off, put it in a coil. We're thinking about it. Yeah.
I'm wondering, because having everything in line would be more efficient, but then you would require more shielding to keep stray AF fields from hitting your sample when you're supposed to be in a zero magnetic field.
Mm-hmm. Yeah, I mean the QDM in theory, I mean as long as you don't go too high, there's nothing there that really can get damaged. So in theory, you can just put an AF coil on it and just turn it off while you're imaging. But yeah, we just haven't gotten around to trying to do that.
Could you use the Helmholtz coils?
They don't go very high. Yeah, they can do like maybe the first couple of AF steps, but yeah. Yeah, I guess at some point you'll start like melting down the metal components, but hopefully, yeah. So we haven't tried it, but yeah, it's definitely a intriguing idea to increase throughput. Right, so you just kind of push a button and it does the whole sequence overnight or something. Anything else? You'll tell all your friends.
Oh, yeah. The quantum, the QEM, it's right up against the sample?
It can be, yeah.
Okay.
Yeah. Yeah, for like interim stuff, a lot of times because we actually want lower resolution, right? Like more of a bulk measurement,
Right.
we put spacers between the sample and the sensor. But
So for example, what's I'm assuming there's a height difference between raw map and upward continued map?
that's right. Yeah, so it's something like 50 microns. Yeah, either like 30 or 50, something like that.
Where's that paper going? It's in review.
What is it? JGR planets. Yeah. Yeah, we didn't get a lower bound, right? This is just an upper bound. We basically found there's no signal, and then we use ARMs to like try to quantify kind of the recording limit. So if we had a lower bound, I would maybe try to take a bigger bite out of things. But yeah, I think it's just kind of consistent with what we see, but I wouldn't say it's like really game changing. But I think it's still a cool result. It's the first result from the outer solar system chondrites. Yeah.
You mentioned the
Yep.
detector again.
This detector?
Oh yeah, what did you use to determine the magnetic field?
Oh yeah, so for the first data point, it was this guy, and the right data point was this guy. So that's the QDM. Yeah, so the detector here is like it's a nitrogen vacancy.
What's the actual sensor?
Yeah, it's a nitrogen vacancy color center doped synthetic diamond. Yeah, it's like kind of this new quantum technology that's it allows you to like optically probe magnetic fields, basically. Yeah.